Let me try to move the screens over here on the side. Okay, hi everybody. My name is Mike Ritz, W7VO. I'm the director, ARRL director for the Northwestern Division up here, also known as the Fire Division. So it seems like half of the division's on fire right now. Looking outside at some really horrible smoke. If anybody has some bacon they want to hang up, just bring it to Oregon. We can take care of your smoking for you. I'm also a assistant EC for the local Columbia County, Oregon here, and I also helped develop some of the training program that we have for our amateur radio operator training. We have before the ARRL had their EC1 course. We had our own course set up to train radio amateurs in basic radio operation, and so I put this program together as a training program for NVIS antennas, which are very important for MCOM. So this is not a highly technical discussion. It's going to be kind of an overview. To kind of let you guys know, I'm sure many of you guys that are involved in MCOM are very familiar with NVIS antennas, but we're going to hopefully learn something here this evening. And this is a presentation I also did for Columbia County Emergency Management. I live in Columbia County, Oregon, about 25 miles northwest of Portland. So let's go ahead and get started. So let's go through our introduction here. Number one is we're going to talk about what is NVIS and exactly what does that do for us. NVIS stands for Near Vertical Incidence Skywave, and it's a phenomenon we're going to be discussing here as we go down. So great, what the heck is it, and really why do you care about it? If you're an MCOM person, you really do care about NVIS, and we're going to talk about why here in a little bit. It's very important for HF MCOM work, and it's basically, for the state of Oregon, it's a very important tool that we have to get all of our messages from our various 36 counties in the state of Oregon. The state of Oregon is about 320 miles by about 320 miles. It's kind of a square, and that's kind of a strange size for radio propagation. So we need to get all of our counties talking to our state OEM office, which is in Salem, Oregon, which is kind of in the middle, a little bit north of the middle, but so it's about 150 miles from any point in Oregon to get to Salem, which is our capital and where our state OEM office is. In order to understand this, though, we really need to know more about propagation of radio frequencies, and we're talking about our radio frequencies below 30 megahertz. This is the HF frequencies. We're not talking about VHF here. We're not talking about 2 meters. We're talking about HF. And what we're talking about is our communications for emergency nets and for digital communications such as Packdoor that we use with Winlink. You guys have had a lot of discussion on Winlink. We're going to talk a little bit about the propagation of how the Packdoor side and the VARA side of Winlink work. So what is propagation? What's the definition of propagation itself? Well, one definition, it's the spreading of something. If you live where I am, propagation could be the spreading of manure. You know, you spread things around. But what we're talking about in specific here are the spreading of radio waves. We all know as hams that radio waves bounce off the ionosphere and give us this thing called worldwide communications and lots of DX. You can work stations here, like that's Bob Valio down here in the corner at the very famous DXpedition at BS7H, where he was basically, this, believe it or not, is a DXCC country that he's got sitting on this rock out here in the middle of the Pacific Ocean. Propagation. There are two main types of radio propagation that we're going to be talking about here that are of general interest to this program. One of them is called skywave propagation, and the second is called ground wave. And we're going to talk about what those are and why those are important to us. In ground wave propagation, radio waves typically travel point to point. They run along the ground and they really don't bounce off the ionosphere. They may bounce off of mountains. They may bounce off of buildings and whatnot, but they're not gonna, they don't bounce up off the ionosphere. They're basically following the curvature of the Earth. Ground wave propagation is typically only good for about 20 miles, and the stations that operate ground wave between them have to be fairly close together with really no obstacles in the middle. And that's really important for our discussion here. Think of an AM radio station during the day. You've got a transmitter over here, a receiving station over here, and you can think about listening to a radio station during the day. And if you can listen to a radio station during the day, an AM radio station in particular, that's all via ground wave communications. And of course, at nighttime, you can get the skip communications, which is skywave, and you can hear AM radio stations that are on the other side of the country. I used to do that as a young kid. Sit there and listen to, be down in Los Angeles and listen to radio stations in Salt Lake City and up in Seattle and in Portland. And boy, that was big time radio for a young kid. Skywave communication signals bounce off the ionosphere and then back to Earth and then back up again in a pattern. Usually great for long distances, but not so good for short distances. And this is really what DX is all about. In DX, you want to have a signal that's able to bounce off the ionosphere, come down to the ground, bounce back up to the ionosphere, bounce on the ground, and just keep going till it reaches its destination. And this is what DX is all about. The distance varies with what's called the takeoff angle. And you can look on this little chart here. It comes off the transmitter, bounces off the ionosphere, hits the Earth, bounces up, bounces down, bounces up, and finally winds up at a receiver. And so what happens in between the ground wave zone and the sky wave zone? And that's called the skip zone. It's called a skip zone because it's skipped. So what we have is you have your transmitter down here. And this is a graphic that I pulled off the internet. You have your transmitter here, and it's sending out a signal, and a big portion of the signal here is ground wave. And once you get out here, you can see the signal starts fading away. If you look at this, the sky waves part of it, it'll go up here, bounce off the ionosphere, come down here and land, and come in down here. But you can see that there's an area here in the middle between the two, between the edge of the sky wave and this first skip zone, which is, or excuse me, the first spot where it hits the ground is called the skip zone. And in here, this transmitter is not being heard. Yeah, because the signal is being skipped. It's either over here or it's back here, but it's not in the middle. And this area here could be the area of typically between 20 miles and about 200 miles. The signal is not being heard. So how do we overcome this obstacle? How do we get signals from one to there? Well, what if we manage to raise the sky waves up to a steeper takeoff angle? So here's a kind of a little theoretical diagram, and shows what the distance is for the skip wave at various takeoff angles. So here we've got a very steep takeoff angle. The signal goes up, bounces off the ionosphere, and bounces down here and creates this level of skip zone. If you have a much lower takeoff angle, say one that's way down here, which is great for working DX, but look how far you go out. Your skyway coverage is all the way over here. Now your skip zone is this big, much, much larger. And this could be now literally hundreds and hundreds of miles. So the idea is you want to get something that's a fairly high takeoff angle, which is not what you want for working DX. You want to be able to work in close. So the way to solve this problem is by using what's called a near vertical incidence skywave NVIS antenna, also known as an NVIS. And as you might imagine, the NVIS antennas radiate almost all of their energy just about straight up, giving coverage from about 20 miles to about 400 miles in range, depending on what the actual angle is. But they work very well for close in. And in our state of Oregon, they work perfectly because any point in our state to the center of the state's about 150 miles. That's a real good sweet spot for NVIS antennas. So here's a NEC chart for a NVIS antenna, and you can see that most of the energy here is radiated pretty much between 20 or 30 degrees on each side of the vertical reference, and very little power out here at the very low takeoff angles. If this was to be a DX antenna like this one, this happens to be for a vertical, or maybe for a 3-element Yagi. I guess it's for a 3-element Yagi at a pretty good height. See, they've got about maybe a 20 or 30 degree takeoff angle here, where most of the power is centered on these two major lobes, and there's a very minor lobe here going straight up at 90 degrees. And here on an NVIS antenna, almost all the power is going straight up, and you've got only within a couple of dB for maybe 20 or 30 degrees on each side. Some advantages of NVIS antennas. They cover the area which is normally in the skip zone, which is too far away for ground signals, yet not far enough away to receive sky waves, which is great for a MCOM, because in MCOM, you're basically trying to send signals from a remote site in a state to somewhere at an OEM office, or maybe to an adjacent state. Here in Oregon, we try to find Pactor nodes that are in Utah, or Idaho, or Washington, or even Nevada, or even California, when we're trying to connect to move our digital MCOM traffic. NVIS does not require any kind of an infrastructure such as repeaters or satellites, right? It's just using the ionosphere. Two stations employing NVIS can establish fairly reliable communications without the support of any third party. Pure NVIS propagation is relatively free from fading, because you're not having this multiple bounce situation. It's just one bounce up and then back down to ground again. Antennas optimized for NVIS are usually low. Here's the good part about NVIS antennas is they're generally pretty lousy antennas. They're not what you'd want to use for DX work. They're not what you'd want to have for your home DX station if you're trying to get DXEC. So simple dipoles work very well. A good NVIS antenna can be erected easily in a short amount of time and by a pretty small team. Even just one person can put up an NVIS antenna. And we've practiced this many times in our simulated emergency tests here in Columbia County, Oregon. Some disadvantages. Well, really, for best results, both ends of the path should be optimized for NVIS operation. You can imagine if you've got a guy at the other end with an antenna with a very low takeoff angle, that means it's also got a very low receive angle. And so he's going to have maybe trouble picking you up if he's set up for working DX and you're set up with an NVIS antenna. So you want to have NVIS antennas at both ends. Doesn't work on all HF frequencies. So we're talking about here is primarily on the 40 meter band, the 80 meter band, ones that you typically use for using Pactor during the day or in the evening. And so care must be exercised to pick an appropriate frequency, right? You want to have something without too much noise and has the correct propagation that you want. And unfortunately, the bands that are good for NVIS, 80 meters, 160 meters, 40 meters, are generally the noisiest. So you've got more noise on those bands to contend with. Due to differences between daytime and nighttime propagation, you really need to have two different frequencies that you can use with NVIS. In order to ensure reliable around-the-clock communications. And here in Oregon, we typically use 40 meters and 80 meters. I'm sure a lot of you guys, these are your primary frequencies that you're using for your MCOM traffic. Examples of NVIS antennas. Yeah, a very low dipole or a fairly steep inverted V work just great. And that's what a lot of MCOM stations use. For NVIS antennas, they give you the correct pattern. A very low horizontal loop works. A horizontal loop that's fairly low to the ground has a fairly high angle of radiation. A low tri-band antenna, a little TH3 Junior that's maybe 20 or so feet up, 15 to 20 feet up, makes a pretty good NVIS antenna. Not so good are verticals. You don't want to use a vertical antenna for a as an NVIS antenna. And you can see the reason is down here is in this pattern chart. You can see that a vertical, because you think of it, it's going right on the end of the antenna, it has literally no power going straight up or at any usable angle for NVIS. You have to get out to about here before you're even 10 dB down from where you started with power. And you can see that the takeoff angle here is optimized for about 20 degrees. This would be a great DX antenna, but not a very good NVIS antenna. So if you're trying to set up an NVIS for MCOM work, do not try to use a vertical antenna. Once again, we're talking about HF operation here, not UHF and VHF. This is primarily for low band use. So here's some examples. Here's, unfortunately, if you're a DXer guy like me, this is what you don't want to have, right? It's a 140-foot tower with nice stacked Yagis on it. That's not going to be a good NVIS antenna. It'd be a great antenna for working the contest, and I wish this was my antenna. It's got a nice 40-meter Yagi up here, and looks like you got a 20-meter mono, 6 or 7 element mono bander here, and you got probably some 10-meter or 6-meter antennas. Oh, great stuff, but not for NVIS. But if you're a DXer, boy, there's your dream antenna setup right there. So what you do want to have is a low inverted V or a low dipole. And there's some examples. Here's a military version here. What they have is primarily about a 20-foot tall pole. They've got a pair of dipoles off of a common feed that are in an inverted V configuration. Here's an example of one that we tried. One of our guys in our Aries group duplicated this and created 40-meter and 80-meter versions on about a 20-foot piece of PVC pipe, and it worked okay. It actually worked pretty good. We had another one that we had that did not work so well. You can also buy these things commercially. DX Engineering sells an NVIS antenna. It's got the balun up here. You see they've got for 2 different bands on a little collapsible mast that they've got. I don't know how much this thing costs, but it's probably not cheap. But if you want something ready-made, there's an NVIS antenna you can buy right from DX Engineering. Think of a buddy pole, right? Get those little buddy poles. You got a nice low dipole, only 5 or 6 feet off the ground. That would be a pretty good commercial version of an NVIS antenna that would give you a fairly high angle of radiation, and would be a commercial product you could just buy off the shelf and for multiple bands. But once again, the problem with these is, I don't know, you'd have to have one that would do 40 or 80 meters, and this that would be you have to get a version that had the correct loading coils on it to do that. You could make your own, right? Here's a homemade one using some PVC pipe and some wire. You got a couple of PVC or wooden poles out here you could erect with some stands. You got essentially a half-wave dipole here, fed in the middle. You've got at the bottom, you've actually got a reflector. So what you have is essentially a 2-element Yagi, which is aimed straight up. Here's another good example. We actually tried building one of these as an NVIS antenna for our local MCOM use here in a set, and we found out that the inverted V configuration for our application here, dealing with about a 55-mile or 60-mile hop down to Salem, Oregon from where we are 25 miles northwest of Portland. This one didn't work so well. We had better results with the inverted V, but once again, your results may vary, and for your application this may be, but you can imagine somebody could assemble this and put it up pretty easily themselves in just a few minutes. Here's another interesting example of an NVIS antenna that uses kind of the same principle, but instead of the single wire down here, they just laid some reflector wires down on the ground. They're using a 7-foot fiberglass mast. They've got essentially a dipole here that's essentially 7 feet off the ground with a little choke and a PVC tee and a little PVC pipe to hold it up, and this basically laid some wires down to make a good reflector. Here's an NVIS mobile version, right? You could take and put a platform on top of your car with a short little mast, and then run these dipoles out at various frequencies. If you wanted to have your mobile MCOM NVIS station, here you are. You think about a vertical, like a Hustler mast or one of those on here. Again, that's not going to be very good for NVIS because these are vertical antennas. The radiation pattern will be really skewed, being it's on a vehicle. But this would work better for an MCOM application than a mobile vertical antenna on a car would or a truck because of the angle of radiation. So that's all I've got here. I'm going to turn this off and ask if there's any questions. Or turn it back over to our moderator, Dan, if I haven't put Dan to sleep. Oh, there he is.
Yeah, you have not put me to sleep. That's a good presentation. We'd like to use the raise hand. We already got one person, Tom, W3TDH, who's got his hand raised. And keep your mics muted until you are ready to talk. Tom, take her away.
Have you had an opportunity to try a Shirley Array? We did that for field day about 5 years ago and worked like a charm. It really did. We filled in the area around us with a lot of contacts. W3TDH.
Yeah, you talk about like a Sturba curtain array?
A pair of parallel dipoles, if I remember right, at about 0.6 lambda apart. So they're working against each other, and up at, between the 10 and 25% of lambda, which is.
Oh, okay. Yeah, no, we haven't tried that. We've tried the inverted V, a multi-fan inverted V, and we tried the dipole with the reflector. What we use at our permanent station is a pole-mounted inverted V with the apex at about 25 feet. And that seems to get us really well for the 50-mile path that we have to have. But there's no reason why it wouldn't work. I mean, if you think about it, even a high Yagi would work. It's just you're not going to get all the power where you want it to be. But with any kind of an HF antenna, you're going to get some power going the direction that you want it, no matter what the takeoff angle is.
Last thing, 2 years ago for our set, because of the grounds and so forth at the facility being mushy and so forth, they told us to go up to the garage roof, and we had absolutely phenomenal results. And thinking about it, it's a large concrete pad with a lot of rebar in it, right under the really low, not super low, about 30 feet off the deck dipoles, and we reached out to the farthest ends of our state. If you think about Maryland, it's a little weird in shape, but we got all the way out to Garrett and down to the Virginia Beach area, and no problem at all. So we were able to cover the whole state. Now we're pretty centered, but it worked like a charm.
Okay, great. So, thank you, Tom. That's a good
garage
idea.
Roof turns out to be a pretty good place.
Yeah. Well, if it's got rebar in it, rebar is a good metal source. So.
Okay, Joe, what do you got there for us?
Good evening, everybody. I'm in New Jersey, central New Jersey, and I wonder if you could comment on the fact that regardless of antenna, some bands seem to be better at NVIS-like characteristics. And the example I'll give you is during the 13 Colonies event, 4th of July, the hardest station for me to get in New Jersey is New Jersey, because he's so close. I begged him to go on 80 meters, and once he did, I had a great copy from him. And it seems like 80 meters, regardless of antenna, is better for closer rather than DX. And just for reference, I have an 80 to 10 meter end fed up in my yard. Thanks.
No, I absolutely agree. And I think in one of my slides, I talked about what we're talking about our antennas for 40 and 80 meters here. We have our MCOM nets during our sets here in Oregon are typically on 80 meters at 30, I think they're on 3964. And our backup frequencies on 40 meters, and typically 80 meters works best for this. That's kind of the sweet spot on this. So I think most people would agree with that. Thank you, Joe.
Okay, anybody else?
Pete's
got his hand up.
I have a question, but I don't know how you put your hand up.
Oh, well, down at the bottom of your list there, if you've got your participants, you click on that. Right now we got 70 participants. You double click on that, and open up a list. And at the bottom of that is where you would be able to raise your hand.
I see a comment. There was a comment that I saw in the chat where somebody was saying a sloper. Think of a sloper as being one side of an inverted V, and that's one of the reasons they do work. Somebody's mentioned a sloper works well for that, and I absolutely agree. It's essentially one half of an inverted V. So I agree with that. So who was next, Dan?
Well, it looked like John was, but who's the lady that has jumped in there? Let's pick her up. She's having a hard time finding that raise hand. Go ahead.
Yeah.
Yeah, and then after the lady, George NG7A is
Okay,
trying.
George.
All right, well, the lady is N1RKO.
Oh, there we go.
Hi, Mary.
And I can do this too. I'm just eating popcorn. The inverted V, what kind of an angle do you put the wire itself at?
I would say typically it's 45 degrees.
45?
The steeper the angle, that you're going to change the feed point impedance pretty dramatically as you get in closer to 90. I have several noise antennas here for my HF stations to pick up noise that gets radiated out of Portland, and I use a steep inverted V for that. But typically 45 to 60 degrees.
Okay, thank you.
Okay.
Okay, I'm going to mute everybody again. We got some people popping in and some noises, so you have to unmute yourself. Mike, you need to unmute yourself also. Again, if you look at the bottom of your display there, you see participants. We're now at 70. And if you click on that, it'll open up a list. And at the bottom of that list, you'll see where you can raise your hand.
Okay, I see a chat question here that says, do NVIS antennas generally need to be used with an antenna tuner? And the answer is, if they're tuned properly, the answer is no. You typically, a correctly tuned antenna can be tuned just fine with the antenna tuners that are located within the radios. If they're properly tested, properly built. The good thing about an NVIS antenna is you don't have to climb a tower to tune it. So there's no reason to have a NVIS antenna that's not correctly tuned where you require a tuner. And I see a note here that says a common misconception that NVIS antennas should only be used at 10 megahertz and lower. And I would agree with that, but most of the MCOM work that we do is at 10 megahertz and lower. And what I'm typically talking about here is that, but Andy is correct. Anytime you've got a signal that and the correct propagation where you can bounce a signal off of the ionosphere, NVIS does come into play.
Okay, was it George who was having a hard time finding that raise hand button?
Yes, this is George NG7A. I just had a comment. Excellent presentation, Mike, and very good information on both the horizontal loops and the NVIS. And the 0.15, by the way, is the maximum spacing for a Yagi antenna, except it's straight up. So that's where that thing. But I just wanted to comment that magnetic loops make excellent NVIS antennas. And they're also very good for nulling out noise. I had a pair in Arizona where we covered the whole state and I could hear better than anybody. And I also, if you tune them correctly, I was able to put regularly a kilowatt through those. And even here in Cedar Rapids, just a couple of weeks ago when we had the emergency and all the antennas went down, I put 3/8" refrigeration tubing in with capacitor. And as long as you have it tuned, it'll take a lot of power and it can hear really well. The only thing is you need to make sure that you're not in the null. You know, when you steer the antenna, you know, you don't have the station you wish to talk to in your null.
Okay. Rather than, let's try to use the raise a hand thing. Let's pick up some of those right now. It's been waiting for a little bit. John, go ahead and take it.
Yeah, hi, John, KG7WFQ up in Washington State, and I've used inverted V dual band with a 40-meter leg and an 80-meter leg as a portable one with a communications vehicle. We would go out. It's very easy to set up with a paint pole and a tripod, and works quite effectively. And you can find the designs for that, how to cut those each leg so they're going to be resonant on those frequencies. If you just Google it, there's also a design. It's very similar design to the DX Engineering one. And there's even a design out there for a 3-band for 40, 60, and 80. And in Washington, our state EOC uses 60-meter net. And so you can cover all 3 bands in an inverted V that you can set up very simply out in the field. But you can find those designs online very easily. Just Google it.
Yeah, for my own personal MCOM, when I'm set out in the field and need to do HF, I have a bumper mount that's essentially, it goes into the receiver. It's got a little vertical mast thing on there. I can put a little portable PVC pipe on it with a 40-meter or an 80-meter dipole, and just run it out to the ground, and it works just fine. Looks a little funny if anybody drives by and wonders what the heck I'm doing, but it does work pretty well for that.
And here in Washington, we have the same problem you have in Oregon. Not only is it the distance from one side of the state to the other, but we have this problem of a mountain range running through the middle. So
Right.
you got to get up and over the mountains, and NVIS works really, NVIS
Right,
works well for
and
that.
where I am, I'm right on the Columbia River, and I've got to go over about a 1,000-foot mountain to get up over to Salem. And so once again, there's no straight line shot. We've got to go up and over to get over there, and it works. You know, we can hear just about everybody from the state, even in the far corners down in Klamath Falls, with our NVIS system.
Hey, just out of curiosity, you the guys that ran the K7 COL RMS gateway?
No, KC7 COL is our call. That's our call sign for our EOC.
And you used to have an RMS gateway as well.
Yes, well, we still do, as far as I know, unless it's gone down. Nobody's been they won't let us in the EOC building until the pandemic's over.
But again, that was the gateway we could hit ideally about 200 miles away from the North Puget Sound area down to there with an NVIS antenna right into the gateway for Winlink. Perfect distance.
Good.
So it works well.
Glad to hear it works. I'll pass that on to the guy that maintains it.
Okay, how we doing? How we doing over the text type area there, the chat? We got some questions over there we can go to real fast.
Well, you have 2 participants with raised hands here, according to what it says.
Okay. Well, let's pick up a couple more. Mary, have you already been in there? Or you got another one? Mary Jane?
I've got another one.
Okay, take it away real quick.
The receiving antenna would have to be in NVIS as well.
That's correct. It's got to be the same on both ends. You don't want to have an antenna on the receiving station that's a low takeoff angle antenna, such as a vertical, and then have a NVIS antenna on the other end. It doesn't mean it's not going to work, as I mentioned that before, but it'll definitely be compromised if you've got a 20 dB loss in the path area that you want to have on the receive side versus the transmit side.
Would they both have to be dipoles or both have to be inverted Vs, or is that?
No, it's what counts is the takeoff angle.
Okay.
In this case, this takeoff angle that counts.
Okay, thank you.
Okay, well, we're stacking up here a little bit. Thank you, Mary. Pete, go ahead and take it. You've had your hand for a while.
Thanks a lot, Dan. Say, Mike, I built an NVIS antenna that's exactly like what was on one of your presentations, the one with the loading coils up by the top. And what I did is I've been operating 13 colonies as Kilo 2 Lima for quite a few years, and we received a lot of complaints from operators in North Carolina, Georgia, Tennessee, Florida, that they couldn't get K2L. So this year, I made that antenna with the loading coils, and I operated as K2 Lima for 13 colonies event. And after the event, I took all my contacts out of my logging program, and I put all the zip codes for all the QSOs that I made into Google Maps, and I mapped the footprint of my NVIS antenna. And son of a gun, it's amazing. That thing has a 300-mile radius. From
Wow.
my location in the center of South Carolina, 300 miles in any direction. And I've got, they could hear me good. Now, I have a software-defined radio. So my receive antenna was a DX antenna. My transmit antenna was my NVIS antenna. And in that combination, I had no trouble hearing them, assuming I was not in their skip zone. But then again, I was trying to get people locally around me to hear me. And it seemed to work really, really very nice combination.
Good. I'm glad to hear that. That's another idea.
Okay, well, looks like we got a Alaska David out there. Go ahead, Dave.
Well, your NVIS antenna helps out a lot. On 80 meters, your reflection point is 900 to 1200 miles away. So if you don't have some sort of shorter bounce, you're not going to make it. And 30 degrees off the horizontal is where you want to put your antenna at the moment. You want it to be 30 degrees from where the center is. So those are my two comments.
Okay, David.
Thank you.
Thank you. Let's pick up Bob real quick, and then we're going to jump over to the chat stuff. So Bob, go ahead and tell us what you got. Bob, N0YWB. Hello, Bob.
Yeah, sorry about that. I couldn't unmute for some reason. Now I hope you're hearing me now. Anyway, just a quick comment. At least in the northern states, we can buy roof rake poles at the hardware stores, scrape snow off roofs. But these are nice 5-foot long aluminum poles that snap together. They make a terrific field mast, lightweight, and for field day and for Boy Scout training. I've made 35 and 40-foot masts out of these poles for an inverted V for NVIS antennas. And another comment about NVIS, most people should be aware of this, that you're shooting a signal straight up to the ionosphere. Your maximum usable frequency will be 10 megahertz and lower. DX, you're skimming off the ionosphere with a low angle, so you can get by with higher frequencies, but any high frequencies higher than 10 megahertz going straight up into the ionosphere is just going to get absorbed.
Good point. Thank you.
Okay. Let's jump over here to the tech stuff over here in chat.
Okay. There's one question about voice on 3970 megahertz and digital at 35885 megahertz. Would you need two antennas so as not to use an antenna tuner?
Well, for that broad of bandwidth, unless you had a, there are antennas you can make. Remember, QST had one. 80 meters is a very special band because it's for the frequency. It's got the broadest bandwidth of any band that the hams have on the low bands. And so having a single antenna that will operate from 3.5 to basically 4 megahertz without having to retune it or change the antenna in some way by changing a tap on a coil or something like that, or changing the length of it, requires having an antenna that's very large in diameter in order to give it the bandwidth required. And there's actually been some articles in QST, and if you ever get a chance to go visit W1AW in Newington, Connecticut, they've actually built one of the antennas where they have a couple of PVC pipes that are essentially holding together some elements that are basically about 1 foot in diameter, and making the antenna electrically 1 foot in diameter by using 4 wires spaced by some cross T's all the way across. And with an antenna like that, I'm not sure you could get all the way from 3.5 to 4, but you can get from the CW band into well into the phone band with that configuration without requiring a tuner. But you know, then if you look around, there are some very large. There you could also design an 80-meter disc cone antenna, where it comes out from a single point, but it comes out in the shape of a cone on both ends. And that would also give you the same effect. But I mean, you're just talking about a lot of wire and a very kind of an almost unwieldy thing. I'm not sure for 80 meters if you could do it in a fan configuration, but that'd be something else you could consider doing, is having two elements that are fairly widely spaced apart, that are one tune for each frequency, but they are going to interact with each other. And so it's going to take a lot of experimentation to get that. Has anybody here ever tried that? And having a single antenna on 80 meters that'll do both phone and digital? Looks like Bob's shaking his hand, yes. You're muted, Bob.
Yeah, there we go. What I did for a dipole at 35 feet, instead of a single wire at 62 feet long on each side, I used 2 wires, 52 feet long on each side, spread about 30 degrees apart. So electrically, it creates a very fat wire, and it'll tune 3.8 to top of the band without a tuner. Stays under 1.8 to 1 SWR, and it works. People think I'm running a linear.
So that's kind of the disc cone thing, right?
No,
just
no,
imagine. Well,
it's more a bow tie antenna.
Okay, bow tie. Okay.
Yeah.
Well, great. Well, I'll have to try that, because I have the same problem here on 80 meters. I have to use an antenna tuner for my station antennas when I'm in CW contests versus phone. And of course, you do wind up, because you have a mismatch, you wind up with a lot of losses. And I've been trying to figure out a way to make my 80-meter antenna much more broadband, and that might be something I could try. I appreciate that, Bob. I'll have to try building one of those.
I've done it for field day, where again, I'll use nylon guy lines to hold up that 40-foot mast, but then from it, I'll spread out 2 wires on each side, about a 30-degree angle apart. And because it's a wide conductor, it's shorter. That's why it's 52 feet instead of 62 feet. And it works. You know, I don't need to use a tuner during field day.
Great. Well, I learned something here tonight too. Thank you.
Okay, how we doing? Bob, you got your hand up? I thought we talked to you earlier. Maybe I'm thinking of somebody else.
He was just the one that was commenting, Dan, so you can probably take his hand down.
All right, sounds good. It's down now.
Okay.
Let's pick up some more over here in the chat area.
Okay, I'm assuming an AN/GRA-50 antenna is a military NVIS antenna kit.
Yes, that was that one diagram I showed. I believe that was the number that was on it. Yes.
Yep. Okay, because there were some comments about that. The
Yeah.
other question is for digital transmissions, mostly OFDM Tactor type. There's a time constant difference between the ground wave and the sky wave, and there's multipath distortion, which can slow the digital thought considerably. Setting a horizontal antenna too close to the ground enhances this conflict. Also, using a vertical antenna, increasing the time constant difference. For a rule of thumb, go as high in frequency as you can below the minimum usable frequency in order to reduce or eliminate this conflict and to reduce the overall signal to noise ratio. And he wanted to just let it. So I assume that's true.
I would have one comment. What we're talking about here is stuff that are signals that would fill in the skip zone beyond the level of where ground wave is and before you get to the skip zone site. And I'm sure in some applications there are situations where signals are bouncing off of mountains and causing interference patterns and time constant problems. And I could see that happening. And once again, as I've said before, your results may vary, but what we're talking about here primarily is beyond ground wave and prior to the skip wave on a DX type skip wave.
Okay. And someone posted the NVIS manual in the chat if anyone wants to download it for that antenna. So,
oh, good. Thank you.
And otherwise than that, there's basically no more questions in the chat.
Okay, I'm gonna have to get off here real quick. I've got an emergency net for Lebanon, Oregon to get set up on Zoom here in the next couple of minutes. So I've got another 5 minutes. I'll turn it back over to Dan, and then I'm gonna jump out of here in about 5 minutes or so, Dan, wherever you, oh, there you are,
Hey,
you're right over there.
I'm here.
But I
I'm
want
here.
to thank you guys. I want to thank you guys for your attention tonight, and hopefully everybody learned something.
Thank you.
Well, your timing is good. It looks like we're wrapping up with all these questions. Anybody else got a quick question for Mike before he has to bail out of here?
Thank you for coming.
Okay, thank you. And I ask everybody to please pray for the poor people in Oregon that are affected by these fires. The state has never seen anything this bad ever. And so we've currently got over 500,000 people evacuated out of even some urban areas in Oregon. And it's definitely not looking good for the state. And I appreciate everybody's thoughts on that. With that, I'm going to say 7-3 to everybody. And Dan, thank you for the opportunity, and we'll talk to you guys later.
Thank you
Thank you
for
very much.
thank you
right,
for
take
coming
care.
on board. Appreciate that, Mike.
Like I say, I got to get a Zoom emergency net set up.
Okay.
7-3.
Bye-bye. 73s. And as Mike goes away and leaves us all here, right? I think it's been a quick, we understand why, presentation, but I think it's pretty well covered. How do you guys feel about it?
Fascinating. Absolutely fascinating. If you've ever used one in the field, it's absolutely phenomenal that it works.
Okay. Alrighty. Well, if this being the case, we have no more questions. Are there any more questions about this presentation or any of the others?
Actually, I've got a stupid question.
There are no stupid questions, believe me.
Because you guys all know so much more than I do. The one thing that I didn't understand when, what was his name, Dan, put up the, in the very beginning where he showed how a signal goes out and you've got the ground wave going out so far. And then if you had a sky wave, it went up to the ionosphere and down. Was he trying to say that one signal would have both a ground wave and a sky wave?
Yes.
Anybody want to answer that?
Yes. Any
Okay.
signal out, regardless of what you're using it for, will have a ground wave and a sky wave. That's what the maximum and the minimum usable frequency is determined by. And you have to figure that out somehow. But yes, any amateur radio signal that we put out with an antenna will have a ground wave and a sky wave.
And was that true at 2 meter as well?
Yes.
VHF and UHF?
Yep. Yep.
There's where a lot of people run into troubles with the 2 meter handheld. They've got a little tiny handheld and a big tall antenna, and there's a ground problem. And there's lots of workarounds for that to improve your signal with your handhelds. Okay, is there any more? Oh, we got a hand up. Russell, take it away.
You mentioned the other, I apologize for this, I'm a little bit late to the game here, but you mentioned the other presentations previous to this one over this course. Are they available? If they were recorded, are they available to view somewhere?
Yes, they are. I'll send them out again. If you got the invitation to this one, I attached the last 6 presentations, a document that gives the links to those.
Excellent, thank you. I definitely want to catch up on what I've missed.
There's a lot. We're in week 7 of week 12, and we've got a lot more to go and a lot more information to get out there, folks. We're having fun, I hope. Okay. Anybody else? Well, we got a lot of noise in the background. I would mute everybody, but we're about ready to close this thing down. So let's give one more call here. Does anybody else got any more questions? Yeah. I got a couple of people who keep time for me. Barry's one of them. Oscar's another. Oscar's really good. He's my gatekeeper. Okay, folks. Let's shut her down. And we'll be here next week, same time, same place, and look forward to seeing you guys here.
73's all.
73, everybody.
73.
Nice program. Great program.
73, thanks.
My
Dan,
best regards as well, folks. Thank you.
73 all.
73s.